Hello and welcome to Math Matters. Why do I need to know this? This is our last episode of Math Matters, and it's been a lot of fun. I enjoy getting the opportunity to talk about applications of mathematics, and hopefully it's been an educational process for all of us. I want to finish today with just a couple ideas from consumer mathematics, things that don't require heavy-duty mathematics in order to understand, but it's good for you to know so that you can kind of plot your course through life, planning your money and so forth. And then kind of wrap up at the end. So let's get going. I'd like to talk to you about annuities. And first I should probably start and tell you what an annuity is. An annuity is any type of account or savings account kind of thing where you make a regular payment into the account and then you get interest on not just you're doing more than just getting money out of this. You're accruing compound interest on this money that you put into the account. Examples would be IRAs, individual retirement accounts, or other type of retirement plans where you're making a regular contribution. Things like whole life insurance policies, not term, but whole life, where you pay on this and then it has some value when you're done paying on it. And even little things like Christmas Club accounts where you put money in monthly and then at December you get the money out and you take that and go shopping with it or something like that. Let's take a look at the timeline of how things work. I want to describe to you how to calculate the value of these things, and to do that, let's talk about how these things would work. You would typically think about in the timeline, and these are months. This is segmented in months. So somewhere here you set this thing up, and then at the end of the month, typically out of your paycheck, you'll make a contribution. So let's assume we're making a $100 regular payment into the annuity, which would be made at the end of the month. Okay? Now, how much is that going to be worth when we're done? Makes sense that it would be about $400, right? I'm making four $100 payments, so my answer should be somewhere close to or slightly above $400. The way to kind of get to the future value of this after a period of time is to take that monthly rate. We've done this before. This is the compound interest formula. It's 100% of what you have plus the monthly rate, and you're going to compound that interest, but in this first month you only draw 1, 2, 3 months of interest on it. So that's raised to the third power. The second payment only receives 2 months of interest, so that's a 2 right there. The third payment only receives 1 month of interest, and the fourth receives no interest at all. It's just the $100 that you started with. And I went ahead and put the 0 there to kind of illustrate what's happening. To get to the future value of this, we have to add these amounts up. So you're adding up things raised to powers. Now, you can do that the hard way. I mean, you get your calculator out and just sit there and hunt and peck all the time. But I'd like to look at things that happen over a long period of time. So I need a formula. I need a shortcut to the answer. So what I'm going to do is I'm going to show you a little trick. This is a cool little trick where we add up things. What we're talking about is when we add up things raised to a common power, we call that a geometric series. And we have a nice way of generating the value of a geometric series. I'm going to show you the trick. This is really slick. Let's say I want to determine what this would add up to. You know, R is some number, and I'm raising it to the 0 power, then the first power, adding it up, and take this to the nth power. I add all those things up. Well, let me call this S. Okay. I don't know what S is. That's what I want to find out. And I'm going to pull a little stunt here. I'm going to multiply S by R. Now what that does is it raises the power by 1. So I'm lining things up here in powers of R, and then I will subtract this from that. So subtract, I'll even put the little bar there. When I subtract these things, I get S minus RS, and I can factor out that S. Over here, the R to the 1, the R to the 2, the R to the whatever, even the R to the N cancel each other out. So I'm just left with R to the 0, which is 1, minus R to the N plus 1. And so to solve for S, I just divide through by the junk, standard little trick. It actually, the way I set it up, ends up being 1 minus this and 1 minus that. But if you multiply by 1 in the top and the bottom, it would look like this, where I subtract the 1 in each case. And that looks a little neater in the formula I'm getting ready to develop. I'm going to use this idea now to calculate the future value of that account. So we go back to this, where I've got all the different accounts, all the different payments put in, and the compound interest that they draw, and I'm going to add those things up. So each one of those has a 100 in there that I can factor out. Okay, and then here is my geometric series. And if you'll notice, that power of R is always one more than the highest power in the series. So this would be a 4, which is actually equal to the number of payments I made. Okay, and then it's just a matter of deciding what the monthly rate is. If I do this with, and there is a little simplification, 1 plus M minus 1 is just M. If I assume a 6% interest rate, that's 6% annual, divide that by 12, then that's 0.5% per month. So my monthly interest rate would be 0.005. And then when I do the little calculation, it works out to be $403.01. Now that means I gained $3.01 from this process, other than just what I paid in. It's not a big wad of money, I know. But now let's think about, I'd like to think about what happens if I try to do this over a long period of time. So first let me say the general formula. Let me just go back and I'll take the 100, make that a P. N is the number of payments. Okay, so here's the formula that I would use to calculate the value of the annuity after so many payments. Let's say, for example, that I pay $100 from each paycheck for 30 years. And I'll say still I'm getting 6%. Okay, so taking those amounts, here's the 100, there's the 0.5% interest, there's the 0.5% interest. When I do that calculation, I end up with over $100,000. Now, when you think about how much I paid in $100 360 times. So that's $36,000 that I paid in. I've almost tripled my money by doing that over a long period of time. Okay, so I'm trying to show you the value of this kind of account. The additional thing to kind of point out about this is how it reacts to small changes. Now, let's say instead of $100, I put in $101. That means I'm going to contribute an additional $360. Okay? So how does that affect the calculation? Well, it raises it by a little over $1,000. So again, I put in an extra $360. I get out an additional $1,000. I could also look at changes to the percentage rate. 1% of $36,000 is $360. However, compound interest works so that I draw interest on my interest, and that snowball effect, if I raise this up to 7% as opposed to 6%, the end value, the future value of this account is $142,330 basically. That's a $41,000 or $42,000 increase. That's dramatic. Okay, so it shows how effective that is by the interest rate. I've actually got a couple summary pages that have those formulas on them that will kind of summarize what we just talked about, and I'll get set up for the next segment. Idea and kind of financial idea I'd like to talk to you about today involves the fair division of estates. Perhaps you've inherited some money, or you've inherited a house or a boat or things like this, and you have siblings, so you have to share it. Well, some things share very well. Money, you take a wad of money. If there's 3 of us, we divide by 3. We each take that amount of the money and we go with it. It's not so easy when I talk about things like houses and boats and so forth. You can cut them into thirds, but then you've destroyed the value of them. You can sell things, but that's not always a good option either. If it's the old family home, you don't want to sell the old family home. Someone needs to hold on to the possession of that in the family. And so the question becomes, how do you divide things up so that everyone feels like they are getting their fair share of the estate? And it turns out there's a nice little mathematical algorithm for doing this that I'm going to take you through. It's very simple. It really just involves addition and subtraction and division and so forth. But it's pretty slick. Let me run this situation by you. Let's say there are 3 heirs to an estate that includes a house, a boat, a car, and then there's $75,000 in cash. Okay, now the cash division is easy. They'll each, we can say, well, you each get $25,000 of that. But let me hold on to that cash for just a moment, and let's talk about how we can divide the estate up fairly. Okay, the first thing that I would do if I'm trying to work this problem is I'd say, okay, I would like each of the heirs to bid on the items, and this will take place in complete secrecy. They won't know what the other is bidding, and I'll show you later that it actually works to their advantage to bid on its value to them, not some kind of inflated value. So we go through and all the heirs bid on the items, and I'm showing you some examples of what those bids could be. Then what we need to do is go through and, based on these bids, determine what they would consider to be a fair share of the estate. And the way we do that is we add up the value of everything according to what they call the value. So for heir 1, we take the values that they gave here, add those up, and then the $75,000 is worth $75,000 to everybody. So we add that up. That makes the estate worth $168,000 to this heir. We're going to share it equally, so we divide by 3, and that gives us what we call their fair share, according to them. We do this with each of the 3 heirs. So we do this across. We add everything up, divide by 3. Add everything up, divide by 3. So they're being fairly consistent here, but they're not identical, and that's kind of important. But this is what every one of them should consider a fair share of the estate. Okay? Then we go in and we say, okay, you bid the highest for this item. It is the most valuable item. You consider it to be the most valuable of the 3 of you, so you get that item. Now in our case here, that would mean that heir 1 gets the house. Heir 2 bid the highest with $7,000 on the boat. And heir 3 bid highest on the car, so they get the car. Okay? You get those items. Now here's the problem. This house is valued at, actually by all of them, at much more than their fair shares. These are valued much less than their fair shares. So what we do is we then use the cash that's in the account to kind of adjust everybody down to the fair share. Okay, so the first person, the house is worth more than their fair share. That means they need to pay some back, and they end up paying the difference, which is $29,000. That's paid into the estate. Okay. Now the other folks paid, received less than their fair share, so we're going to make up that difference in cash. Okay, so heir 1, when we subtract, they would receive $48,000 paid from the estate. That's removed from the amount of cash that we have on hand. And heir 3 received the car, I think. That the difference in their fair share, what they consider their fair share, and the car's value, what they consider the car's value, is $47,000. So we take that out of the estate, pay that to them. And when we're all done with this, we still have a little bit of money left over. There's $9,000 left out of the cash. And so the next step is easy. Divide 9,000 by 3. Give each of the people left, give each of them what's left, $3,000 to each of the heirs. So what does that really give? What do they end up with? That's kind of the point of this. The first heir gets the house, which they value at $85,000. They had to pay some cash, but they get $3,000 of it back for a grand total of, in their mind, $59,000. Okay, now that's $3,000 more than what they considered to be their fair share. The second heir got the, I think it was the boat, received some cash and received the additional cash. That additional cash is over and above what they consider to be their fair share. And then the third heir, the same thing happens. This is a nice system because everybody ended up getting more than what they considered to be fair. Everyone should be happy with this arrangement, and which is nice. That's a good system. It's a good way to kind of handle things. Even beyond that, it's a good system in that it discourages folks from bidding artificially raising the price of something to make sure they get it. Everyone has to play honest or they're going to get caught, and I'll show you how that works. Let's say that the first heir really, really, really wanted the house. So they gave this exorbitant price, this exorbitant bid on the house. Even though they really thought it was valued at $85,000, they bid $200,000 on it. Okay? Now watch how this affects their totals. Their fair share now is going to go up, right? When I change this to $200,000, the value goes up here, and then when you divide by 3, it goes up. So their fair share is inflated as well. Okay? The rest of them stay the same. They were going to get the house anyway, and so they still get the house. What changes now, though, is how much is paid to the estate. If this is $200,000, this is now a pretty big sum, right? This is way over and above what they consider their fair share. So they have to pay quite a bit back to the estate. And what that does, it puts a lot more cash on hand for the estate. Okay? Everything else is as it was, but what changes is instead of taking the amount, $9,000, dividing by 3 and getting $3,000, now when you divide by 3, you get $28,500. So that's paid out, and watch what happens to the value here with each of the heirs. Okay? And what I've done, instead of the $200,000, I used the actual value, what they thought it was actually valued at. They end up with a lot less than the others. And what they've done is they've cheated themselves out of, they did get the item they wanted, but they've cheated themselves out of actual value of the estate. This is a remarkable little system for doing this. Chances are at some point in your life you might encounter a situation like this. Now you kind of have an idea of how to handle the mathematics of it. I've summarized the algorithm for this in a couple of summary pages, and I'll get set up for the last little segment. The last thing I'd like to do with you today, since it's our last episode, is I would like to kind of wrap things up with some encouraging words. Now, I realize at this stage of the game, you're probably getting ready for finals, you may be getting ready for finals, and you may even be a little sick of mathematics at this point if you're finishing out the semester. But I would like to encourage you to follow up and take some more mathematics. And I have a couple reasons for telling you this. We've already demonstrated that we can handle some very tough situations with the mathematics that we find in the general math courses. We spent a semester here looking at things like that. It's also true, though, that you can get into some fairly routine situations that have tough mathematical answers, and that's the kind of thing that we handle in the upper level courses. For example, here's a very easy problem. If I say, okay, what are all the solutions to this equation? Well, you probably realize by now that's a line. It's a linear equation, so the graph of this is a line, and the solutions are all the points on that line. That's pretty easy. A graphing calculator can do that for us. However, if I ask the question this way, I said, what are the integer solutions to that equation? That is a lot less exacting, and a lot of the solutions here will not work. They have to fall along an integer lattice here, like these points do. This actually occurs at 1, 1. This occurs at -2, 3. Those are integer solutions. They're not always, not everything on the line, though, will work for this answer. And so we're getting into a field of mathematics called discrete mathematics. And that requires some further study. Although that's a very simple kind of question. Here's another one. Let's say I want exact solutions to this quadratic equation. Now, you folks have probably know the quadratic formula. Some of you even, I had some kids yesterday singing me the quadratic formula, which I thought was pretty cool. We have a way to do that, and I'll show you the graph. We can use quadratic formula. We could even factor this one if we needed to solve it exactly. However, if I take any one of those powers up above 2, like if I make that 2 a 3, that becomes a very difficult thing to solve symbolically. Even this one, which has nice answers, it has nice integer answers, -2 and 1. If you ask me to do that symbolically, that all of a sudden becomes a pretty difficult problem because I don't have a cubic formula. I have a quadratic formula. I know how to solve linear things. But something like that is actually kind of tough. We can talk about numerical solutions. We can talk about some different ways of trying to factor that. But as a rule, multiplying is much easier than factoring. And that's fairly difficult to factor. Okay? That's, by the way, is the idea behind public key encryption, that you have this big long number that is the product of 2 primes. It's easy to multiply the primes together. It's very difficult to divide that composite number into the 2 primes. And that's a lot of our national security is based on that very idea right there. Here's something else. If we look at 2 lines, a system of equations, linear equations, I say, okay, what are the solutions? Well, we've talked about actually in this program ways of solving that, getting exact solutions to that. The solution will be this point where the 2 lines overlap. However, if I jump above the power of 1 on any one of these things, like I make that x cubed, make this x to the 4th, all of a sudden this has become an extremely difficult problem to solve exactly. And it really doesn't get much better as you go up to higher level mathematics. This is just a hard problem. Okay, we can do it graphically. Obviously, I can graph these things, and I can numerically try to isolate that point. And there are other techniques for doing that. But exact solutions are very difficult for nonlinear systems. So, and these are the kind of things that can pop up in day-to-day applications. I mean, not everything is linear. That's just the sad fact of things. Here's another example of a very tough problem. It sounds very simple. We have a bakery that makes 5 different types of fudge. It sounds like something you would ask out of just being naive. How many different ways can we fill a package with 12 pieces of fudge? I've got 5. I can make them all one type. I can make them all the other type. I can make half. I mean, you start thinking about all the ways to do this. There are a lot of ways to do this. That is a very difficult question to answer. That's also something we handle in a field of math called discrete mathematics. We have counting techniques for doing things like that. But it's a little difficult. And if I go back and I say, well, okay, let me put a restriction on that. Let's make sure we have 1 of each type in the package. Then it gets just that much tougher to kind of figure out, okay, well, how many ways can you do this? You certainly don't want to have to try to list them all out, process of elimination, because the answer could be up in the thousands, 10,000s, whatever it is, okay? So this is some fairly difficult mathematics to deal with, although it's very simply stated, okay? The other kind of approach, the other thing I would say as far as why I would continue to encourage you to study math, I think we jump the gun sometimes when we're studying, and we make this assumption that because we can't immediately find some application of things, that it's not really very useful. Okay? I couldn't disagree with that attitude more. Okay? The problem sometimes is not in the mathematics, it's in our understanding of other sciences or other applications, the actual content where it could be applied, the area where it could be applied. I always think back, a great analogy for this would be the space program. Okay, the space program really kind of was driven initially by this fear of the Soviet Union dropping bombs on us from space and all this. But even after we had kind of won the Cold War, we continued with our space program. And people say, well, why do we care about that now? We won. But you have to look at the benefits that have come from that space program. Cell phones are a direct benefit. Cell phones were actually developed through technology developed by NASA in getting people to the moon and things like that. Velcro is designed after stick tights in nature. But where did they use that? Well, they used it on the space, in the space capsules, because you can't lay a pencil down in space. It floats off. So they needed a little piece of Velcro, and they'd stick it to stuff, okay? So it's not always the mathematician's fault or the mathematics' fault that we don't see the application. Sometimes we have to educate ourselves in other areas, okay? Terry Wilcutt, I heard him say this one time. Terry Wilcutt is an astronaut who graduated from Western with a degree in mathematics. We're very proud of him. He said, mathematics is the common language of the sciences. And that's true. If you're working in the science area and you understand the mathematics, sometimes it would be very difficult for a biologist to talk to a geologist, for example. They may not have common things there. But a mathematician, in some sense, in some way, could probably talk to both of those people, as long as we're working on some kind of problem together. I really would encourage you not to give up, even if you've had a rough time this first time through. There's very cool stuff out there. And it just takes a little bit more education sometimes to find it. I've summarized a few of those little comments that I talked about, and I'll flash those pages up and we'll come back and we'll wrap things up. Well, I want to thank you for tuning in. I hope you've checked out several of the episodes this semester. I hope they've been helpful to you. I hope they've been educational. And I hope they have served your purposes, helped you in class, and helped kind of expand your horizons as far as what math is good for. There's a lot of things out there. I still would like to hear your input on things, and I would encourage you. We have a webpage that will flash up in a few minutes. Use me as a resource if you wish to tackle things about applications, and I'm always looking for new ideas along these lines. So I want to thank you for your time. I think I've done all the damage that I can do. Hope to see you again.